If we have a rational point as a tag, we get 1. So let's design a mesh function that tells us what the subinterval structure is going to be. That minimizes the contribution of the rectangles that have rational tangents. That's what we're going to do. And here is my mesh function. The mesh function is this. So if C is one of the rational numbers, that's the mesh function. It's 1 if C is not 1. Okay? Here's what the mesh function is all about. If I have a tag point, say the ith tag point, the subinterval that the tag point is in itself has to be contained in the interval defined by the mesh function. So if I pick the tag point Ti, I add the mesh function evaluated at Ti, and I subtract the mesh function evaluated from Ti. And then I insist that whatever subinterval I use, whatever partition I create, subinterval that's containing the ith tag point has to sit in something. Intuitively, if bad things happen around the point Ti, what I would like is for M of Ti to be small, mesh fine, small, so that this is just a tad below and this is just a tad above. So the base of the rectangle in which Ti sits doesn't contribute very much to the overall integral, right? In other words, where the function is poorly behaved, if I have a tag point where it's poorly behaved, I want to minimize. I want to sort of stamp that out by having a very small subinterval there. The mesh function allows me to control the size of the subinterval at bad points. The bad points, from the standpoint of the Dirichlet function, are the rational numbers, because then the thing shoots up to 1. If I can somehow make the contributions of the rational points negligibly small, then I would find the overall integral to be 0, and that's what it is in the rate function. So that's what we know the integral to be, right? I'm trying to set up a Riemann sum that does the same thing. You see where I'm going with this? I would like to surround the rational points with really, really small subintervals so that they don't amount to a hill of beans when I take the overall sum and estimate the integral. That's what I'm going to do. If I don't do the mesh function trick, if I just try to set up a Riemann sum, every once in a while, I'll get a partition that has a rational point, and the value of the function is 1, and there's some positive measure down here. I'm not going to get convergence. I'm going to get that business where it's not 0. I'm stuck away from it. But if I can force it to be small, I'm in business. So let's see if we can do that. All right. Well, whatever partition I pick, it's a finite number, right? And suppose I get finitely many of these bad points, ill-behaved points, the rational points, where the function value is 2. is it pretty clear that the sum of the function, this is delta, the Dirichlet function, delta of ti, delta xi, I equals 1 to n, for any n, is going to be less than or equal to, certainly it's going to be greater than or equal to, it's less than or equal to, well, the worst thing that can happen is the partition picks up all of the rational points, but it doesn't even go that far because it has to be finite. But certainly if I hit every rational point, this thing has to be less than, right? Okay. So what I'm saying is if I go from 1 to infinity, and I have, how big could delta xi be? Remember the mesh function? I go up and down from the tag point. It wouldn't be any wider than twice this, would it? This is what you add and subtract from the tag point to get the maximum width of the base rectangle. So if I put in twice epsilon over 2 to the n plus 1 times 1, that I claim that inequality is true. Is there any doubt about it? This, I go up and down by the epsilon over 2 to the n plus 1. So that's a rational plus that, same rational minus that. So the width, this width from here to here is never any greater than twice that, right?
What is multiplied by 1?
It's the value of the function at each rational. It's the value of the function at the rational. So, and this is on beyond any partition. This is every rational. So I know this is true. This is only some of the rationals, right? Here's the function. If ti happens to be rational, then it's 1 times this width here. So I'm going way overboard. I'm taking every bad case, every rational, and of course the function is 1 at every rational. So that's true. All right. What is that sum? This sum is epsilon, 1 to infinity, divide by 2 top and bottom. Would help if I used I instead of n, of course. Sorry, I wrote n up there, and then I switched to I down here. Okay. What is the sum of the geometric series whose first term is 1/2 and constant ratio is 1/2? What? Yes, sir. It's 1/2 over 1 minus 1/2. So that's epsilon. So every headstock Kurzweil sum is stuck between 0 and epsilon. Let epsilon go to 0. What's the interval? 0. So this thing will integrate the Dirichlet function. I would really like it. I'm not sure we can even do this. I can't do it right now off the top of my head. Do you know what the function sine 1 over x looks like? Well, suitable scaling. Huh? If I took the absolute value of sine 1 over x, then it would be a positive. These lobes would all be pushed up, right? That thing has an area. You're not going to integrate that with Darboux or Riemann, right? Because as soon as you have a partition element that starts at 0 and goes out, the sign is wiggling too fast. It doesn't matter how wide that thing is, you'll have you'll have a max of 1 and a min of 0. It's sort of like the Dirichlet function, but just at one end. Everything out here, if you went from like 1/2 to 1, you could do it. You can do it, but you can't do it if it goes to 0. And I wonder what I wonder if that's stuff Kurzweil integrable and what the integral is. We should research that. Well, anyway, we'll do something else on